So, question paper major 2025, and it's the paper 5, region 3. Question number 1. Number 1 says Grignard reagents have the general formula RGMX, where R is the hydrocarbon group and X is the halogen. The Grignard reagent C6H5MgBr is used as an intermediate in the reaction between the bromobenzene and ethanol to prepare 1-phenyl ethanol. An organic solvent, ethoxyethane, is used. This question includes some of the difficult names which you might have not you haven't studied them before, you never came across them before, so you have to keep looking at these names and remember the names whenever they ask any question about them. The equations for the three reactions that take place during the preparation are shown. The reaction 1 has this equation, reaction 2 has this equation, reaction 3 has this equation. The preparation involves the following steps. Step 1, set up the previous shown in figure 1.1. Let's see the figure here. This is a figure which we have to understand. Although this figure was never used in your lab experiment in your AS level, but you might have seen this diagram before. For example, you have seen that condenser. You must have seen the this round bottom flask in the diagram before, and this one is a tap funnel, which just the bottom end looks more like the burette. If you remember, the burette has a similar type of the picture. I'm just considering the lower bottom end of the burette. Okay, so this is a diagram 1.1. Figure 1.1 with approximately 1.25 gram of Mg powder and 5 cm cube of the ethoxyethane in the round bottom flask. They are using initially these chemicals in the round bottom flask. In step 2 at 0. Instead of reading through all the words, I will just go to the question and see what we need to find. This is a table in which some of the substances are mentioned. They have also mentioned the densities of these compounds, the boiling points, and the hazard. The question is, use the information table 1.1 to suggest why the following safety precautions are used. Point 1, wearing chemically resistant gloves. Okay, now we have to understand why chemically resistant gloves are supposed to be used in the lab. For this purpose, we will just look at this table. Now, in this table, we see the hazards are mentioned for the different chemicals. Definitely, the gloves are worn on the hands, which means we have to see those hazards which may attack on our hands. So we find this particular hazard, which is vulnerable for our hands. So we can say wearing chemical resistant gloves are required because bromobenzene is supposed to be we consider that bromobenzene is supposed to be the skin irritant. We will write bromobenzene is a skin irritant. Then second point, using a fume hood. We are looking at the safety precautions and do remember that such type of the questions come frequently. We have to understand the reason of using the safety precautions, and the hazards caused by the chemicals. They may ask you one thing and they give you the explanation for that, or they will ask you the explanation for the different purpose. So we already have the hazard say, we just need to link that hazard with a purpose. The using a fume hood. So if you remember, you must have seen this fume hood in your labs. Have you ever seen fume hood before?
No.
Um, this is something I'm
Or
just
maybe
going.
it's there and I just didn't know it was called that.
I'm just going to draw a small diagram. It's basically kind of a glass shield, I would say. This is a glass shield, and within this glass shield, they put a lot of chemical bottles. The chemical bottles are present inside of this glass shield, and the experiments are performed within this glass shield using two arms.
Oh.
They use two arms. One hand goes from one side, the other hand goes from the other side. And inside of that, we have this point where they put a vacuum.
Yeah, okay, yeah.
This vacuum is used to just remove all the vapors which are collecting inside this hood, inside this hood.
Mm-hmm.
So since the reaction is such a type that the vapors are toxic, because we see they are toxic. So these toxic fumes have to be eliminated from the hood. So that's why using fume hood is used. So why are we using the fume hood? We are using because the reaction involves the toxic fumes, or that's it. Or you can say the toxic gases are produced during the chemical reaction. Toxic gases, like this whole apparatus which we see here. This whole apparatus is something like it is present inside a fume hood. That's what we can understand. A fume hood contains the whole of this apparatus. All right.
Okay.
And the purpose of fume hood has been clear. It is used to remove the toxic gases produced during the chemical reaction. All right. Then moving onward, part B says dry apparatus and reagents are essential for steps 1 and 3, suggests how the glassware shown in figure 1.1 should be dried before use in step 1. Okay, they are asking you so they're asking you how do we dry the glassware? What do you know about the glassware? What is glassware here in figure 1.1?
It's the round bottom flask.
It's a round bottom flask. This is a glassware. The condenser is a glassware. The tap funnel is a glassware, and the whole of this connection is a glassware. All of them are glassware, except for, I would say, these bungs. These are not glass. They are not made up of glass material, but the rest of everything is a glass material. That's what they call glassware. Now, how do we make them dry? How can we dry them? Do you know any reason? Do you know any way of drying them?
Uh, Leaving them out. Uh,
Sorry,
um,
heat them out.
yeah, leaving them out. Like,
Okay, leaving them out.
yeah,
If you try to leave them, it will take a lot of time to
yeah.
get dried. So you have to make it faster. So basically, this is a very simple way. We have an oven inside the chemical labs. Within the labs, we have some ovens. These are basically specified. They are purpose-built ovens only to put the glasswares inside of them. They are not for the cooking purposes. They are just there. They have some shells. They are provided with shells. Like we have one, two, three different size of shells. You can increase the spacing. You can remove some shells as well. You can take them out in case if you want to put a very large size glassware inside. So these shells are there, and you put the glasswares on them, and you can set the temperature by yourself. You can set the temperature, let's go starting from 0 degree centigrade till some all the ovens have their own capacity. You can even take them till 300 degrees centigrade or even further. But it's not that much required. Even if you just put for almost 50 degrees centigrade, that's sufficient. So that you can easily grab the apparatus, or just wear the glove, any thermal gloves, and take out the apparatus for the use. So the purpose, the way we can dry the glassware is by warming in oven. All right, it is clear.
Yeah.
We just
Yeah, it
warm
is.
them in the oven. Then second, the ethoxyethane contains a small amount of water, suggests how the water can be removed from the ethoxyethane before use in step 1 and 3. The ethoxyethane was mentioned over here, and the whole of these steps. Uh, they said the organic solvent ethoxyethane is used. They are using this solvent, ethoxyethane. Now, ethoxyethane is an organic compound, but it also contains some amount of the water present within that. And if you look at this table, they required us uh, required us to go through this table as well, because here in this table we also find the boiling points. The boiling points are mentioned, and we have the ethoxyethane mentioned over here, and the distilled water is mentioned over here. Like they both are added into each other. Now, if they are added and we have the different boiling points for them, 100 degrees centigrade and 35 degrees centigrade, we can say that we can separate these two components from each other simply by having a different temperature set. That means what that technique is called, in which we separate the substances on the basis of their boiling points.
Evaporation.
Evaporation is simply the conversion from liquid to gas. That's evaporation. But I'm asking for the technique in which the boiling points have to be kept in mind for two or more components.
Oh, wait. It uses the same apparatus as what?
Not the apparatus, the method, the procedure, the name of that
Yeah, but
procedure.
like it uses kind of like it's one where they collect gas from one of
You
them and the other one remains.
you have studied this thing in the petroleum topic of the O levels. Petroleum separation, if you remember. You used to get the different fractions of the petroleum.
Distillation.
Exactly. That was
Oh,
called the fractional
distillation. Yeah,
fractional
I was
distillation.
describing the apparatus that they use.
Okay. So fractional distillation is basically applied here to separate the water from the ethoxyethane. Now, part C says, figure 1.1 show the apparatus for step 1 to 3. Draw a labeled arrow on figure 1.1 to show where the water enters the condenser. Okay, now you have to indicate where the water enters the condenser. So that means you must remember the diagrams. Basically, all the questions related to diagrams are associated with the O level knowledge. If you have the O level knowledge of the experimental apparatus and experimental design, then you can easily give correct answer. Experimental design. That was the topic then. So this is a condenser you see here. So, and these are the inlets or outlet of the water. So do you remember from where do we put the water? From the downward side or from the upward side?
Um, the upper.
If you have, No, they don't work. If you have to revise the literature which I sent you of the paper 5, do read that out. So water is entered from the inside. Water is in from this inlet. The purpose, the reason behind what's the reason why we put the water inside from the lower? Why not from the upper? The reason is that if if you put, let's suppose if I say the purpose of condenser is to cool down the or condense the vapors inside the condenser. That's the purpose of using the water. Now, if you put the water from the upper point, it will quickly move out from there because it is moving uh, down towards the gradient. I would say towards the gradient. Like water moves fast from high altitude to low altitude. Is that so?
Yeah.
Water moves quickly from high altitude to low altitude. Now, if it moves swiftly from high altitude to low altitude, then it will take less time to condense the vapors present inside the condenser. So it will not fulfill its purpose. Our purpose is to condense the vapor inside the condenser. So that means the water should take a longer time to move inside the condenser. It should take longer time. So if it moves upward, it will take longer time. Do you get the idea now?
Yeah.
More time will be taken when it moves from downward to upward. It is said to be called against the gradient. The movement of water is against the gradient, and it takes more time to come out from this outlet. So that's why we use the water inside from the lower point. Uh, this asks you to draw the labeled arrow, so I have just uh, put the arrow along with the label water in. Then part 2 suggests why solid Z is used. Solid Z. That solid Z is mentioned over here. If I zoom it, do you see that these are something? What do you consider what these solids are supposed to be?
Um, is it the same as the solids that like absorb carbon dioxide or something like absorb
Though
gases?
those are chemicals. Those are chemicals. We are not looking at the chemicals here. This is a part of the apparatus. So let me tell you. Now these are my notes of the O levels. So I'm going to show you that part here. This is the glass beads. These are the
Oh,
glass beads over here inside the condenser. So we also call it as fractionating column or condenser because both they now this one is a fractionating column because they were using the condenser. Along with the condenser, they had this type of the picture of the glass beads. Although the purpose of glass bead in the fractionating column is different here, they have mentioned that glass beads. Let me highlight that part. Okay, glass beads in the column provide a large surface area for the condensation. This is the purpose of the glass beads. But that is in the fractionating column, not in the condenser, which means you have to understand why the glass beads are used with the condenser. So I would say that the purpose of condenser is to the purpose of condenser is to condense the liquid and within the solvent ethoxyethane, they said that the ethoxyethane contained water within that, and we had to remove that water. We have to remove the water from the ethoxyethane. We have to separate on the basis of the fractional distillation. So when the water is gonna be removed from the con- condenser, then these solid particles they will help to uh, remove the water. We would say they prevent the water getting into the apparatus. That's what we can say. These solid particles will prevent the water molecules moving back into the apparatus. Prevent water going back to apparatus. All right. Then part three. Give one reason why the apparatus does not have a bung at the end of the tube. Why? Okay, basically we have this apparatus, and in this apparatus there are multiple reactions being carried out uh, in these three different reactions, and every reaction has different chemicals being used. So if we look at the step set uh, startup apparatus shown in figure 1.1 with approximately 1.25 gram of magnesium powder and 5 cm cube of ethoxyethane in the round bottom flask. And then step 2 says 0.05 mole of liquid of this C65 bromine to the round bottom flask, drop twice and using the tap funnel, leaving the direction 1 and leave until direction 1 is complete. Then dissolve this ethanol 15 cm cube ethoxyethane and add this solution to the round bottom flask using the tap funnel, leave until direction 2 is complete. So you see that there are multiple steps included and there are different chemical reactions carried out within the round bottom flask. So we say that let's suppose if we close this end of this condenser, then doesn't it seem that the water inside produced must be trying to escape out of the apparatus? And if we stop that water coming out or escaping from the apparatus, it will definitely create some pressure. The pressure will build up inside the apparatus. So to reduce that pressure, the bung is not used. The bung is not used at the end of this condenser only to lessen or only to prevent or avoid the pressure buildup in the apparatus. All right.
Yeah.
So we'll say to avoid pressure buildup in the apparatus. Okay. Now moving forward. In step 1, approximately 1.25 gram of magnesium powder is needed. Outline how the student should accurately weigh by difference using a weighing board so that the exact mass of magnesium transferred to the task is known. Include a results table with appropriate headings ready for the student to fill in. Now, this thing or this part of the question will take your test of the knowledge you had in your AS chemistry lab. If you remember, you used to measure the mass of any particular solid for the chemical reaction, and you used to have the headings in the tabular form.
Yeah.
So you used to have a container containing any solid particles. You used to measure that mass on the weighing machine, And after transferring that solid into the chemical reaction, you used to again measure the mass of the same container along with the lid or without the lid, whatsoever you used. And that difference gives you the exact mass you used for the experiment. So you have to recall that knowledge, and you have to put the right you have to use that right headings here in the sequence, like in the sequential form. So what would you write? And do you know what this wing board is?
I think it's just a way of measuring the mass.
Yes, it's a glassware. Again, it's a glassware, and this glassware is designed in such a way it looks more like a board, and it can be used to put uh, the apparatus can easily set on the weighing machine easily. It does not it does not uh, uh, it doesn't remain unstable, and also you can add and remove the solid from this weighing board. You can easily add and remove the solid out of inside and out of the glassware. So you have to write the tables here. So what would you write what would you write here?
For the table or the steps?
Yeah, you have to construct a complete table along with the steps.
Okay, so for the table, the first one would be the mass of no, like mg powder plus um plus the container. It's in a container, right?
It
Plus,
is a container, but you can use complete name, or you could simply use a name this port
okay, mass of mg powder plus boat
plus port
slash grams.
slash gram.
This would be like M1, for example.
Hmm.
And then you will have mass of boat itself without the mg powder. Just mass of boat.
Just mass of board. Okay.
In
Are
grams.
you are you sure that you have completely transferred the magnesium powder?
Um,
Okay. One thing that is left behind in the previous title is that mass of magnesium powder to the board before transfer. You can also write that before transfer.
okay.
Before transfer and mass of board plus. Now, as I said, are you sure that you have completely transferred the magnesium? But I would know that you are not sure, which means that leftover amount will be called as residue. Do you remember that word residue?
Yeah.
So you will write mass of board plus magnesium
Residue.
residue, or just magnesium powder residue. That both mean same, magnesium residue. And after transfer, after transfer slash gram. So these will be two titles. Now what's next?
Then mass of mg in grams.
Mass of mg, and you can state this thing in terms of transfer, mass of magnesium transferred or
Yeah.
used, or both can be said, transferred or used. Mass of magnesium or used, because we uh, they already said the use the word transferred. Exact mass of magnesium transferred to us. So mass of magnesium transfer use and slash, that is gram. That will give you the difference of the first and the second. Okay. Now moving forward, E says use the information in table 1.1 to determine the volume in cm cube of bromobenzene used in step 2. MR of bromobenzene is 156.9 gram. Okay, you have to use the information of the table. The table includes the names of the different chemicals, including the name of this compound. And you have the MR value of this compound 156.9, and you have to calculate the volume. I would say that bromobenzene has the information of density and boiling point in that table. I'm not writing the values, I'm just saying that density and boiling point is mentioned in the table. Now you have to calculate the volume. You have to calculate the volume over here, and you are also given the MR of this compound. So, what step will you include to find the volume? And density is usually given in gram per cm cube. This is the density of every
Yeah.
compound. I will take you to this table, and here we can find density is in gram per cm cube, and this is bromobenzene. Mentioned the value of. Do you need to use the value of boiling point?
They gave us no.
Okay, we will only use the value of density 1.50.
They, they gave us the moles in step two.
They gave us the moles in step 2.
Yeah,
Yeah,
for
yeah, we have to move to step 2 exactly. Uh, 0.05 mole. That's also required 0.05 mole. So I will put that value over here. We also have the mole 0.05 from step 2. Now use all this information to find the volume.
okay, so we find the mass using the MR and mole.
Okay.
Mass
So
is equal
formula
to MR.
more, yeah. So rearranging the equation, we have the M is equal to N into MR. Moles are 0.05 multiplied by MR, and 0.05 times MR is 156.9.
7.845 grams.
Hmm.
7.845 grams.
10
Wait,
point, I need to have the value with me as well. 845. Okay, now this is the value of the gram. What else we need to do now?
now we use the density formula.
Density is mass over volume, and
Yeah.
we have the mass. So, okay, we have the mass, but we need to find the volume. So, volume will then be equivalent to V is equal to mass over density. The mass
Mhm.
is 7.845 divided by density value is 1.50. Density value is 1.50. So, it is equivalent to 5.23. So, this will you right here 5.23. Is this clear?
Yeah.
Then F part, the bromobenzene is added dropwise in step 2. So just one reason why the bromobenzene is not added all at once. So if we go back here in these steps, it was mentioned in the second step that you have to put this bromobenzene compound in the down bottom flask dropwise using the tap funnel. The tap funnel is indicated here. This is the tap funnel and it is put inside. Do you know why we are just putting dropwise, not as a continuous flow? And okay, the table can also help you to understand that they said bromobenzene. Bromobenzene is mentioned to be a flammable compound as well.
Yeah.
So it is flammable. So what do we think? Why it is being put dropwise?
To avoid like um
If it is flammable, it means that the reaction is very violent. The reaction
yeah.
is a violent reaction. So we can say that to prevent reaction to be very violent, we can write that to prevent reaction
Or vigorous? Is vigorous
becoming,
also?
yeah, that's fine. To prevent reaction become vigorous or violent, that's fine. Then G says suggest why magnetic cylinder is suitable piece of apparatus to measure 40 cm cube of hydrochloric acid in step 5. Why do we need to use the measuring cylinder to to measure HCl? Now, do you remember the different apparatuses used in all levels to measure the volume? Like
Yeah.
it was rated with one factor. What was that factor? Pipette, etc. Pipette, burette.
Why they were used?
Yeah, why we use these different apparatuses?
They had like graduations for burette and measuring cylinder, but the pipette was like a fixed volume.
It has a fixed volume, whatever was written and mentioned on it. It could be 25, it could be 15, it could be whatsoever. It is fixed,
Yeah.
but mostly it is 25 cm cube. The burette has mostly 50 cm cube. Now, marine cylinder also come with different volumes. Now, if you remember, they had the different accuracies as well.
Yeah.
The burette has the highest accuracy because it has the least error.
Mm.
Highest accuracy and least error. On the other hand, pipette has slightly less accuracy than burette, and measuring cylinder has the least accuracy over here. Measuring cylinder has a least accuracy. So why are we using a very least accurate apparatus to measure the HCl? Why don't we use a very accurate apparatus to measure the HCl?
It's faster.
40 cm cube can faster. Okay, it's a faster method, but we uh, don't you think that it's more related with the volume that is basically excess volume of the HCl that needs to be considered? Add 40 cm dilute hydrochloric acid to the round bottom flask so that the reaction takes place. Basically, they removed this apparatus, the whole of this apparatus was removed, and this one was also removed. After that, they put the HCl in it. After that, they put the HCl. So now it doesn't matter the speed of transferring is counted. Here we say HCl is basically taken in excess only. That's why they do not need to use a very accurate apparatus to measure. HCl is in excess. Okay,
How do you know?
because less accurate apparatus is used. Less accurate. Makes it less accurate. That's why. All right.
Yeah.
Okay, Jenny, I have to say my prayer here. It's So we had done up to this point. Now next part, H. The separating funnel used in steps 6 and 7 is shown in figure 1.2. The final product is 1-phenyl ethanol is in the ethoxyethane layer. Separating funnel is mentioned here, drawn here. State whether beaker A or beaker B contains a layer with 1-phenyl ethanol. After step 7, explain your answer using the information given in table 1.1. All right. Now, this is a picture of the separating funnel, and this separating funnel is being used to separate the phenyl ethanol from the other compound, which in this case is the H2O. H2O is the other solvent, and phenyl ethanol is in the ethoxyethane. If you remember that topic of KPC from your paper 4, from your theory, KPC, do you remember that topic?
Yeah.
It was the concentration of the solute in
No, an organic solvent, and then
organic solvent, yeah, organic layer or organic solvent, divided by the concentration of the same solute in the aqueous layer. Now, although this is a formula that we used, but it can also be inverted. This equation can be inverted by putting aqueous in the numerator and the organic in the denominator, and that all depends upon which of these two layers will be present in the lower portion. We have these two layers. One layer can be represented somewhere, I would say here, and the other one is in the one layer is here, another layer is here, somewhere here. Now, it all depends upon the density. Which compound has more density, that will be present in the
the
downward portion. More density, the more density will be present in downward portion, and the less density compound present in the upper portion or the upper layer. Okay.
yeah.
Now they are asking us to find which beaker, whether A or the beaker B. There were two beakers used. I will go back to the step and see what they put in the beaker A and what they put in the beaker B. So here, open the tab of the separating funnel and run the lower layer into the beaker labeled air. Okay, now lower layer is in the
A.
beaker A. Lower layer is in the beaker A and the upper layer is in the beaker B. Now, how do we know which compound among the which compound among these two is in the upper or lower portion? We have 1-phenyl ethanol. This is the solute. This is the name of the solute. 1-phenyl ethanol, and the solvents are H2O, and the other one is ethoxyethane layer. Now, they are asked you to use the value or the detail from the table 1.1. So table 1.1 in here, ethoxyethane layer, 1-phenyl ethanol. This is the solvent name, 1-phenyl ethanol. The density is 1.01, and the other solvent is distilled water. The density is 1.00. That means we have these two different solvents present for that one particular solute. All right.
Water. Why not ethoxyethane?
Oh, my mistake. Yeah, you're saying exactly. You are correct. The solvent is ethoxyethane. Yeah, this is solvent.
Isn't it one phenol? What? Isn't it one phenyl ethanol and ethoxyethane?
Ethoxyethane is a solvent, organic solvent, and 1-phenylethanol is the solute or the product, I would say. This is a solute. These two are solvent, distilled water and the
Oh,
ethoxyethane.
so the one phenyl ethanol is dissolved in one of them,
Both,
either
in both of them.
distilled water. And well,
It's dissolved in both of them. This is the concept behind partition coefficient, KPC,
yeah.
that the solute is dissolved between the two immiscible solvents. Ethoxyethane and distilled water are immiscible into each other, and they both are containing the solute. All right?
Yeah. But the question is like states whether beaker A or beaker B
Okay,
contains the
yeah,
layer with
exactly.
one phenyl. So
Ex
if they both have one phenyl ethanol in them, then
hmm. Here comes the thing we have to identify the densities of the solvents, not the density of the solute.
oh,
We have to look at
okay.
the densities of the solvent because they are the one which are carrying the solute. So the density of the ethoxyethane is less than the density of the distilled water, which means ethoxy is above and H2O is below, right?
Yeah.
Okay. Now they also said that the lower layer was added into the beaker A. According to the steps, they said that the lower layer was in A, and we know the lower layer is H2O, and the above layer is of ethoxy ethane. Clear?
Yeah.
So that means H2O is put in beaker A, and ethoxy ethane is put in beaker B. Is that clear?
Yeah.
Now they ask you. Now coming to the question, what they ask you, you have to tell. You have to tell which beaker A contains a layer with one phenyl ethanol after step 7, that they also saying step 7. So after step 7, the final product, which is phenyl ethanol, it was in the ethoxyethane layer only, not in the H2. There was the I would make a diagram, simple diagram, H2O in the lower layer and the ethoxy in the upper layer. According to them, the product, I'm not writing the full name of the product, I'm just writing product. According to them, the product was completely moved to the organic layer. It was completely separated into the ethoxy layer. It was no more in the H2O. There was zero amount of the product in the H2O. All right.
Okay.
So they are asking in which beaker they will add the product, in which beaker they will add the product. So according to this information, the product is present only in the ethoxy layer, and the ethoxy layer is less dense than the water, and according to that, ethoxy is in the upper layer. Upper layer is put in the beaker B, and the lower layer is put in the beaker A. So what would you give the answer?
B.
B, exactly. So it will be beaker B, and the explanation is that density of ethoxyethane is less dense than, you can write H2O, or you could write water.
The the product is dissolved mainly in ethoxy ethane because it's
Hmm.
non-polar or what?
Yeah, we could say that it must be a very much non-polar in nature. They said that the product came in the ethoxy layer after step 6 and 7. So what step 6 says? Transfer the contents of the round bottom to separating funnel, allow the liquids to settle so that two layers are formed. Open the tab separating funnel, run the lower layer into bigger. It means that it's all on the basis of the polarity of the compound. Um, it might not be matching any polarity with that of the H2O, and that's why it was not in that. They have already stated the amount present of the product. They says the final product, one phenethanol, is in the ethoxy layer. They have not mentioned anything about H2O.
Oh,
Nothing is present in H2O.
they gave us the answer then, basically.
Hmm?
They basically gave us the answer then.
Yeah, they basically gave the answer, and they are, or you could say they are giving you the clue to find the
Yeah.
answer. All right, so this is done. Now moving to next part, I. This is I, and this is part one. I part one. The overall reaction can be represented as shown in figure 1.3. This is bromophenyl. This is ethanol. Ethanol. I will write here. Uh, bromobenzene. This is bromobenzene. This is ethanol. And this is the name of the product 1-phenyl ethanol. Because the symbolic representation might confuse you, the skeletal formula might confuse you. So this is 1-phenyl ethanol. At the end of the steps 8, 2.17 gram of 1-phenyl ethanol is obtained this product. Determine whether bromobenzene or ethanol is a limiting reagent and hence calculate the percentage yield of 1-phenyl ethanol. Show your working. Now here we have this final equation. We have this final equation, and we have to identify which of these two, the bromobenzene and ethanol, is a limiting reagent. So how would we identify limiting reagent? Do you remember that topic? How do we identify the limiting reagent? What factor is that? Which factor is applied to identify the limiting reagent?
Sorry, I forgot.
The amount. What do we call, like, how do we define the limiting reagent?
I always got confused in whenever they would talk about limiting reagent, so I'm not really sure.
The definition, I will just write down the definition because this is what will that will help you. A limiting reagent is the one which is consumed earlier. That is called limiting reagent. Number two, which controls the amount of product. Number three, which is present in lesser amount. Is that clear?
Yeah.
These are the definitions, or these are the explanation of the limiting reagent. And reagent means reactant. Reagent means reactant. So which of these two, bromobenzene and ethanol, is a limiting reagent or limiting reactant? That means which of these two is present in lesser amount. In lesser
Not just
amount.
the moles for each one.
Exactly. We must know the moles of each of these two. That will help you to identify. So that means you need to calculate the moles, or now the moles of the bromobenzene and the ethanol. So the moles of the bromobenzene, do we know that or do we need to find that?
We need to. Oh wait. We do know this. Wait, they gave us right. Yeah, 0.05.
Exactly. The moles is already provided. That means you do not need to calculate it. So 0.05 mole is already mentioned. So I'm just going to write that here. 0.05 moles. What about ethanol? Do we have the moles or do we need to calculate it?
No, we need to calculate it from 1 phenylethanol.
Okay. We need to calculate it from 1 phenyl ethanol. I
Yeah.
suppose we.
Oh wait. Yeah. No.
Okay, look. If we come back to the steps, what do we see about the ethanol? We see that they used this much volume of the ethanol. They used the 3 cm³ of the ethanol here, and in the table
We
we
have
also
density.
have we also have the density of the same, so 0.788.
Hmm.
So we have the volume, we have the density. We can use these values.
Yeah.
So 0 point density of the ethanol is 0.788. Density is 0.788 gram per cm cube. The volume is 3 cm cube. And then the formula is already there. CH3 CHO, which means you can also know the MR of this compound. So density is mass over volume, and we need to find the mass. Mass is equal to density times volume. Density is 0.788 times volume is 3 cm cube. 0.788 into 3. It is equivalent to 2.364 gram. Now, after this, the next formula which we can use is mass over MR. Mass is given 2.364, and MR can be calculated from here. It is 24 for the carbon plus 4 for the hydrogen plus 16 for the oxygen. So 46? No,
44.
44. It's 44. So put 44 over here.
Sir, the analytic chemistry, is it used in paper 5 or paper 4?
Analytical chemistry is majorly in paper 4, but very
Oh,
less extent in paper 5.
okay.
Have you done the NMR part?
The
Have
what?
you have you studied the NMR and the chromatography which I shared with you? The Google Drive.
No, I'm still like dealing with organic.
Oh, okay. Do complete that part as well, the analytical part, because it will also carry roughly around, I would say, 10 to 15 marks.
Okay. Yeah,
Okay, so.
I did solve a chemistry paper, paper
Hmm,
4 yesterday, and like almost like when what you reach like towards the end, it's just all organic,
hmm,
almost
hmm,
like paper.
hmm.
Yeah.
That includes the organic part of the AS level as well, the
Yeah.
basis of the AS organic. Okay, so the moles calculated for the ethanol are 0.0537 mole. Now
Hmm.
compare this value with the already calculated value for the bromobenzene, which is 0.05. So which value is less?
The bromobenzene.
And limiting reagent will become,
The bromobenzene.
yeah, this will become the limiting reagent. So this is what we have found from here. They ask you to determine which one is the limiting reagent. So we would say that the limiting reagent is the bromobenzene. And after that, your calculation will be credited here. Like the calculations I have done for the ethanol, these will be credited in this part. Now after that, you have to find the percentage yield of the 1-phenyl ethanol, which is the product here. You have to find the percentage yield of this one. Do you remember the formula of the percentage yield?
Actual yield divided by theoret, or was it theoretical divided by actual, multiplied by 100?
Repeat, please.
I think it was actual, or yeah,
It
actual.
is. It is actual Weber theoretical. Always remember that the value in the numerator will be less and the value in the denominator will be higher. Theoretical value is always higher because it does not involve any kind of loss. It does not include any kind of error. That's why. That's why theoretical value will always be larger than the actual value. Multiply by 100. Now, actual value, where is the actual value, where is the theoretical value?
Um, the actual value is probably given to us. Yeah, it's
Actual value is given because they said in this part at the end of the step A, 2.17 gram of 1-phenethanol is obtained. This is the actual. Actual means the experimental value. So it is
yeah.
2.17. Now, what about the theoretical?
We have to use density and volume to find that, or wait, we don't have the volume.
now
Mm,
here, now here you should apply the limiting reagent concept and stoichiometry. The stoichiometry or ratio method and the limiting reagent concept. This is the product which we are finding. This is the product, and these were the two reactants. This is reactant one, and this is the second reactant majorly. So, according to this chemical equation, we find that all of these are present by one ratio. All of them are one ratio. This is one ratio. This is 1 mole, and 1 mole. All of them. So we need to use the value of the mole of these two reactants with that of the product. But between these two reactants, one of them is a limiting reactant, the other one is not. And as I defined, limiting reagent is the one which controls the amount of the product. This is the limiting reagent. And here we found bromobenzene to be the limiting reagent. So the number of mole of the bromobenzene will be the mole of the product. All right.
yeah, okay.
So 0.05 mole will be the moles for the 1-phenyl ethanol as well. So
Sir, if I found the moles of one phenyl ethanol using the 2.17 grams, I can just do the moles divided by the moles of bromobenzene.
um, that you need to see that which one is the reactant and which one is the product. You cannot go in the backward direction.
What?
What your question is?
No, like I use the mass, the actual mass. I'm saying if I converted it to moles, the actual grams, use the moles of bromobenzene instead of converting moles to grams. Like, is that
It is
fine?
a conversion. It is a conversion of moles to gram, but how much mole should be there? That is calculated using the ratio method.
I'm saying, can I use it in moles, or do the values need to be in grams?
Gram. Basically, if they have given the value in the gram over here, 2.17 gram, then definitely you need to use the same value in gram here. And
Okay, but if
always remember the yield is always mentioned in gram, never in mole. But they can be in volume as well if the product is a gas. They can also give the amount in cm cube. The percentage yield would either be calculated if they give the amount in either gram or volume,
yeah, okay.
not in concentration, not in moles. So 2.17 gram was the actual yield, and theoretical yield must be calculated. That for that purpose, multiply this 0.05 mole with the MR of the product, because we have calculated that this product has 0.05 mole. So the formula says N is equal to M over MR, and we need to find the mass. So M becomes N times MR. So 0.05 multiplied by MR is 122. 122 into 0.05, this becomes 6.1 gram. So 6.1 gram is a theoretical yield. Multiply by 100.
35.6.
Okay, so 35. Do remember that how many decimal points are mentioned in the information. They have used 2.17, and this is the number of the decimal point you have to use. So you will write 35.
35.5.
Yeah. Mm, Let me see again. Third. Okay, one more thing. This is also another answer. This is in one decimal point. So can you we always use the least number of the decimal points in the given question. So the answer will be in one decimal point according to this MR value. So 35.6 is the correct answer. 35.6%. Okay.
Yeah.
Now the part two. Suggest why the infrared spectrum of the product detected the presence of a C double bonded O peak. This is carbonyl.
Hmm.
Why the carbonyl peak was detected in the product?
The product?
Yeah, in the product. Like, why do we see the carbonyl peak in the product? Although the product is phenyl, one phenyl ethanol, but this
Is
is the
it still?
structure. This is the structure of the one phenyl ethanol. And this is not the only product. There is also magnesium ion, there is also bromide ion. But we do not see anywhere we do not see the carbonyl group. So that indicates we need to see other substances as well. So the other substances are bromobenzene, ethanol, magnesium element, and hydrogen ion. Where is the carbonyl group present in all of the whole reaction?
Ethanol.
Ethanol, exactly. We have the carbonyl group in ethanol. That indicates that although it's a reactant, it's not a product. So why is the peak of ethanol is indicated in the product? What do we conclude from here?
There's some ethanol that's mixed with the one phenyl ethanol or something.
We would not say mix, but we can say present. The
Yeah.
ethanol is still present. It is still unreacted at the end of the reaction. It is
Not
unreacted
all
amount.
of, not, Not all of the ethoxyethane. Wait, does ethoxyethane have?
Did you not check that we calculated the amounts of the bromobenzene and ethanol over here?
Yeah,
And this was in greater amount than the bromobenzene. That's why we labeled bromobenzene to be the limiting reactant. If this is
yeah.
limiting reactant, what this reactant is called? Do you know that name?
No.
That's called XX reactant.
Oh yeah, excess, but I didn't.
That
Okay.
means this is a reactant. This is a reactant that is not completely reacted. It is unreacted. That's why it is still present in the chemical reaction as a product, unreacted amount of the reactant. So we would say unreacted ethanol is present in reaction. Okay,
Yeah.
and that ethanol is containing the carbonyl group. Now we have just finished the question one. Question one is completed.
Yeah.
Now moving to the next question, and in almost most of the papers, we always find the graph paper. In most of
Yeah.
the question, we have the graph paper. That means you have to do the working on your graph paper along with me. And I will just skip some of the parts to save the time because that just requires some calculations. I will just go to this point, give two reasons that explain why the use of iced water in step 4 decreases the rate of the reaction. Iced water, that means very cold water is used here.
Mhm.
Iced, and this is also relating to the theory which you studied in the organic chemistry when there were the formation of the dyes. The azo dye was formed. The azo compound were formed using the ice water, if you remember. So they also use the ice water to slow down the chemical reaction. Now they are saying transfer 10 cm of the reaction mixture to one of the small conical flasks containing the ice water and indicate to record the time, shake the small flask. So basically, the two reasons for the ice water or the two reasons for decreasing the rate of reaction is that number one, the water itself is being added that dilutes the solution. It dilutes the, you can either say uh, dilute the solution or dilute the concentration.
Concentration.
And number two, that the temperature has been decreased. Temperature is reduced. The reduced temperature lowers the rate of the reaction. You know that rate of
Yeah.
reaction is directly proportional to temperature. So if and that is related to the effective collision frequency. Effective collision frequency of colliding particles. When the temperature is higher, they have higher kinetic energy. They frequently collide with energy equal to or greater than activation energy. So that's all we have already studied in the AS and the O level. So you will apply that concept. You just need to say the reason. You do not need to explain again. Then B says describe the observation that is used to determine the end point of the titration. Okay, now we need to go through the step to see how do we find the end point. Uh, Direction is mentioned here. This is ester, this is water, this is the hydrolysis reaction, if you remember in AS, hydrolysis, in which the ester is broken down using the water in the presence of the acid to make the carboxylic acid. and the alcohol. Now, the progress of the reaction is determined or monitored how the concentration of acid changes with time by checking how much concentration of the acid changes. A portion of the reaction mixture is removed every 5 minutes and titrated with sodium hydroxide. A final titration is carried out after 180 minutes. Step 1 says add 70 cm³ ice water to seven separate small conical flasks, few drops of phenolphthalein. Phenolphthalein is pink and alkaline, colorless in acid. Use a Magus render to transfer HCl into large conical flasks. Add ester to the large conical flask, swirl and flask to mix the contents to a stopwatch. Transfer reaction mixture to one of the small conical flasks containing the ice water and indicator to record the time. Now, do you see they have used the word indicator here? The indicator is being reacted with, or you could say it is being mixed with which compound? It is being mixed with the HCl. All right. HCl initially indicator is mixed with the HCl and indicator's color is colorless in the acidic condition, right?
Yeah.
But after that, in the step 5 they added the NaOH, the alkali, and in the alkali, the color of the indicator becomes pink. So the endpoint must be the formation or appearance of the pink color. So we would say appearance appearance of pink color, but that pink color must be permanent because if you add less amount of HCl, the color will keep on disappearing. But the moment the color becomes permanently pink, it will indicate the endpoint. Appearance of permanent pink color. Is that clear?
Yeah.
Okay, then next part C. The results of the experiment are shown table 2.1. Vt the titer at a given time t. V infinity is the final titer at t is equal to 180 minutes when the reaction is assumed to be complete. Table 2.1. Definitely, in such cases, you have to complete the readings because this is also a very frequently asked question where you have to complete the whole table. Complete table 2.1, give you answer in column 3 to 2 decimal points, 2 decimal places, and you answer in column 4 to 4 significant figures. So decimal places is different than the word significant figures. Okay, now here, how would you complete the first row?
Is V infinite 80, 180 or what? Or did
Okay,
they?
okay, read the column. Column 1 says time in T, which is minute, and these are the times in the minutes 0, 5, 10, 15, 20, 25, 180. The second column reads titer, VT, and in unit cm cube, and we have these volume 12, 16, 22, 23, 46, 48, and 45. So V infinity is said is the final titer. They said it's a titer. V infinity is the final titer, and this is the word titer here. But the time is 180 minutes. So the time is mentioned over here. So what do you conclude from here? What does in V infinity would indicate?
So 45.70.
45.70. Very good. This is V infinity volume. Very good. So after correctly identifying, you have to do the calculations over here. So you can just write down the values and I will be writing on my side
Okay.
and it should be in 2 decimal points. They said that put in 2 decimal points. Now take the logs values, log of 33.70. This gives you answers in multiple decimal point, but you need to use 4 significant figures. So although the value is 1.5276299901, but I will use only 4 significant figure. That makes 1 digit from here and 3 decimal points, and that must be rounded off. 1.528. So apply this rule and do the rest of the calculations.
Why not 1.53? Why is it? Why is it
1.5.
3? Yeah.
Okay.
Because everything else is 2 decimal places.
They said here 4. I said you look at the
Oh,
words significant figures and look at the word decimal places. These are
yeah.
two different words.
Yeah.
After that, you have to plot the graph, and after plotting the graph, the question 3 will come. So I will first draw the graph here. I will try my best. It should be correct.
The good thing about paper 5 chemistry is that they give us the scales. It would have been worse
They
if they
also
didn't.
they also they also give scales in paper 4 in some of the questions. They do give.
Yeah, some, but like most of the no paper 4 as in the oh no, because back in the ATP paper in IJCs we had to like find the
Hmm.
value. We had
Hmm.
to scale it ourselves. So but sometimes it was annoying to find and it would take too long.
Hmm. I have just also plotted some of the points by myself, and this is what I see here. The graph should be a straight line, but which point becomes anomalous here? But Where do you find the anomalous point here?
The anonymous point was this one, the one that's supposed to be on 10. On time 10.
At time 10 minutes. Okay.
Yeah.
If I try to make something like this,
It would be harder on the.
mhm. It's still not a straight line because I'm using my hand for this purpose. So you are correct. It becomes very much far. The time at 10 minutes, it becomes very far. Now, what does and we have to identify why this thing is occurring, why the anomalous point is there. Circle one point in the graph that you consider to be most anomalous. Just one reason to explain the anomalous point you have circled. Assume no error was made in the experimental value of the title. Now, this value is kind of very down from the actual value, and it's also left from the axis. Left means less time, and down means less value of log. So, less value of log and less time. Why we need to see that at 10 seconds, the time is less here, less time. And the value of the V log is also less, which means this difference is less. When the difference is less, then the log value is less. Now, why the difference is less? Because the VT value, which is a tighter value at particular time, it should be more increased. The value of the VT has increased exponentially. Anomalously, the value of the VT has increased. That's why we find less this difference. VT was tighter at a given time. So if we go back to this part where the formation was being carried out, we can say that the actual time of the sample removed in step 4 was higher than recorded time. So the titer volume is more than the required. The actual time of the sample removed in step 4 was higher than the recorded time. This is the that's why we have the higher VT value. VT value is higher. That means just give me a minute, please. Okay, we say VT time is higher because uh, although we don't need to write because actual time of sample removed, that is basically tighter. Removed means tighter. And in step 4, was higher than recorded time because we did not properly recorded the time properly. And step 4, it says transfer 10 cm reaction mixture to one of the small conical flask containing the ice water indicator. Record the time. The time was recorded higher. More time was recorded. That's why the VT was is the time recorded is a higher. Is that clear?
Wait, so VT increases because the actual time of sample removed in step 4 was higher than recorded time?
Yes, yes, because we did not properly record the time. We mistakenly recorded a higher time.
Well, what do they mean by assume no error was made in the experimental value of the titer?
Like other errors are supposed to be omitted. No other errors. Uh, Assume no error was made in the experimental value of the titer. Uh, Titer is like we are calculating the volume, but we are this titer means calculating the volume, but we are not calculating the volume. We are calculating the time. We are calculating the time, not the volume, according to the statement. That's what they're saying, that no error was made in calculating the volume.
Oh, okay.
No error was made in calculating the volume. Instead, the error was made in calculating the time. Clear? Then part 4, determine the gradient of your line of best fit in figure 2.1. State the coordinates of both points you use in your calculation. These must be selected from your line of best fit. Give the gradient to three significant figures. Okay, so you have to find the gradient. The gradient, as you know, is m is equal to y2
One.
minus y1 divided by x2 minus y1, right? Is this so?
Yeah.
So use any of your values and find the answer, whatever you find from there.
Sir, for these type of questions, there's a range, right?
Yeah, there exists the range.
Okay. 5 and 1.467 is 1 point, and then the other one is 20 and 1.288.
Give me your coordinates here.
5 and 1.467.
5 and 1.467. Are these y-axis value?
One
Are
is
these
the first one, the 5 is x, and then the y is 1.467.
okay?
And then the other one is 20 and 1.288.
288.
Be
So
significant
it
for
should be 20 minus 5 divided by, I hope, uh,
no 1.288 minus 1.467.
So it is 0 minus 0.011. Three significant figures mean up to 9. 0.0019. The equation of straight line in figure is shown. Use the gradient determinacy to calculate the value for k in per second. If you were unable, then use the value minus 0.0312. They are using the exposed value. This is not the correct answer. So we have to find the value of the k here. This k value, this k over here. And
Yeah.
use the equation of straight line. The equation of straight
Mm-hmm.
line is y is equal to
MX
mx
plus.
mx plus c. Now over here, m is the gradient. Okay, and x becomes t here. X
Yeah.
becomes t. X is equal to t. So minus k t over 2.303, and now uh,
We'll equate this to the
m
gradient value.
k becomes m here. No,
The entire of it is right? Except for t, because t is x.
t is x. So
Negative k divided by 2.303, all of that is the gradient.
hmm minus my negative k divided by 2.303 is equal to gradient. That is right.
Yeah.
And we have to find the k from here. So k and this whole thing is equivalent to k is equivalent to gradient into 2.303 multiplied by minus. It is whole thing in minus. So you have to put the value which you have calculated in the gradient. It was minus 0.0119. So minus 0.119 times 2.303.
I got 0.0275.
0.0, okay, there's slight mistake. 0.0, but you are getting 2.3.
0.02.275.
Where am I mistaking? Like the value is 0.0119. It should be multiplied. It should be multiplied with 2.303.
Yeah.
But I am getting, okay, fine, good. 0.027. And what should be the number of significant figures? From here we can see they are using three significant figures. So 0.0274 up to three significant figures. Then E, use your graph figure to state whether you consider the result to be reliable. Give a reason for your answer. So is our calculation, is our graph reliable? As we can see that here we had the anomaly. The anomalous point was there. So because of this anomalous point, we cannot say the graph is reliable. It's not reliable. It's not reliable because of the anomalous point. All right.
Mm-hmm.
Then last part, K increases with temperature. A second graph is carried out at a high temperature. So sketch a suggested line of best fit on figure 2.1 for the second experiment. So second experiment is done at a higher temperature. When the temperature is increased, the rate of the reaction increases. That means the temperature for that particular reaction should be lesser. So all these temperatures should become lesser. These values become lesser. So over here, if the time is increased, and at the same time, you should know the steepness also becomes the steepness of the curve also becomes more. It becomes more steeper because then the effect of the temperature is on steepness, so more steeper. So how would you plot that line?
It would be a line lower than the original,
Okay, lower line. Uh,
like under the original.
I would say that
Does it start at the same point?
it would start from the same point. Starting point will be the same. If this is the intercept on the y-axis, we have to use the same intercept point, and it should start from the same, and it will be more steeper like this. It's more with negative gradient. It's a more negative gradient with the same intercept.
Why is it curved?
Steepness, the steepness is indicated here.
Why? Wait, don't we just draw a linear line?
Okay, wait, yeah. If you draw the linear line, how would you make it?
I would just draw it straight down. Is it supposed to connect to the end of the other one?
Maybe not. Since the value will decrease, so more negative gradient, something like this. My mistake. I am using the writing pen like this.
That's what I meant.
Hmm.
Yeah, that's what I meant.
So it is more negative gradient. Okay, so this paper has been finished now. Uh, I hope I have clarified you most of the things. We will
Yeah.
now practice